Good day and welcome to our in-depth analysis on quantum supremacy. I'm your host, and today we're diving into one of the most fascinating and controversial topics in modern science and technology. In the next 25 minutes, we'll explore what quantum supremacy really means, examine the major claims and counterclaims, and critically assess just how close humanity is to achieving this milestone. The United Nations has designated 2025 as the International Year of Quantum Science and Technology, coinciding with the 100th anniversary of modern quantum mechanics. But behind the celebrations and bold headlines, a complex story unfolds, one filled with remarkable achievements, contested claims, and profound implications for our future. Let's begin with a clear definition. Quantum supremacy, or quantum advantage, as some researchers prefer, refers to the demonstration that a programmable quantum computer can solve a problem that no classical computer can solve in any feasible amount of time, regardless of whether the problem has practical value. The term was coined by physicist John Preskill in 2011. Though the concept dates back to Yuri Manin's and Richard Feynman's proposals in the early 1980s. Feynman famously remarked, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical." Achieving quantum supremacy requires two key elements. First, the engineering feat of building a sufficiently powerful quantum computer. And second, identifying a problem with a superpolynomial speed up over the best possible classical algorithms. Dennis Mandish, CTO of quantum cybersecurity company Crypt, describes quantum supremacy as a calculation demonstrated on a quantum computer that is impossible for any classical digital device. He compares current quantum computing milestones to AI's GPT-1 moment. Significant, but just the beginning of a revolutionary trajectory. To understand quantum supremacy claims, we must first grasp how quantum computers fundamentally differ from classical ones. Classical computers use binary digits or bits, representing information as either 0 or 1. Quantum computers, however, use quantum bits or qubits, which can exist in a state of 0, 1, or a combination of both. A phenomenon called superposition. This property allows quantum processors to store and process exponentially larger data sets. As Mohammad Usman, head of quantum systems at CSIRO, explains, think of it like a mouse trying to find its way through a maze. With classical computers, the metaphorical mouse has to try each path one by one. With quantum computing, the mouse gets supercharged and tries every possible pathway simultaneously. There are multiple approaches to creating qubits, each with advantages and drawbacks. 1. Superconducting qubits used by Google and IBM. 2nd, quantum annealing, D-Waves approach. 3. Semiconductor-based qubits pursued by Intel, Dirac, and SQC. 4th, photonic quantum computing developed by PsiQuantum, Xanadu, and USTC. A critical debate in the field concerns qubit quality versus quantity. As Usman notes, a quantum chip made up of thousands of low-quality qubits will be unable to perform any useful computational task. This is because qubits are extremely sensitive to noise and environmental disturbances, which reduce their reliability or fidelity. The solution? Quantum error correction techniques that use many imperfect qubits to encode a single high-fidelity logical qubit. Most major quantum developers are now shifting focus from raw qubit counts to creating these more stable logical qubits. Now let's examine the major quantum supremacy claims of recent years along with their contestations In October 2019, Google announced that its 53-qubit Sycamore processor had performed a calculation in 200 seconds that would take the world's most powerful supercomputer approximately 10,000 years. This calculation involved sampling the output of a random quantum circuit, a task specifically designed to showcase quantum advantage. Google's announcement made headlines worldwide as the first demonstration of quantum supremacy. However, IBM quickly challenged this claim, arguing that with optimized classical algorithms, the same calculation could be performed in 2.5 days, not 10,000 years. This dispute highlighted how the goalposts of quantum supremacy can shift as classical algorithms improve. In December 2020, researchers at the University of Science and Technology of China, USTC, demonstrated quantum advantage using a different approach. The photonic quantum computer, JIUSANG, implemented Gaussian boson sampling with 76 photons. They claimed this would take a classical supercomputer 600 million years to simulate. While this achievement received less mainstream attention in Western media, it represented a significant milestone using a completely different quantum technology than Google's superconducting qubits. Most recently, in March 2025, D-Wave announced what they called the world's first and only demonstration of quantum computational supremacy on a useful real-world problem. Published in the journal Science, the research showed D-Wave's advantage to annealing quantum computer performing magnetic materials simulations in minutes that would allegedly take nearly 1 million years on classical supercomputers. D-Wave CEO Dr. Alan Baratz stated, "Our achievement shows without question that D-Wave's annealing quantum computers are now capable of solving useful problems beyond the reach of the world's most powerful supercomputers." However, this claim was quickly contested. Joseph Tyndall, a quantum physics researcher at the Flatiron Institute, led a study showing similar calculations performed on a laptop in just 2 hours. The claims of supremacy are not really true and far more nuanced than that. Tyndall told the New York Post. Miles Staudenmeier, another Flatiron Institute researcher, explained that D-Wave's comparisons were based on state-of-the-art classical methods from 2024, not accounting for rapid advances in classical algorithms. These competing claims and counterclaims reveal several critical issues in quantum supremacy reporting and research. The most glaring inconsistencies involve the claimed speedups. D-Wave's million-year claim versus Tyndall's 2-hour demonstration represents a discrepancy factor of over 4 trillion. Similarly, Google's 10,000 years versus IBM's 2.5 days differs by a factor of 1.5 million. These enormous disparities stem from different assumptions about classical computing capabilities, algorithm optimizations, and problem specifications. They highlight how quantum supremacy claims often rely on comparing against specific, sometimes outdated classical approaches. Quantum supremacy demonstrations typically use different metrics and problem types, making direct comparisons difficult. Many focus on highly specialized problems optimized for quantum advantage rather than practical applications. As NYU physics professor Dries Sells notes, firmly establishing quantum advantage is a tricky business. The boundary between feasible and infeasible classical computation is constantly shifting as new algorithms and hardware emerge. We must acknowledge that companies like Google, IBM, and D-Wave have financial incentives to promote quantum supremacy achievements. Press releases often emphasize breakthrough claims while downplaying limitations or contestations. Media coverage frequently frames quantum development as a race or competition rather than collaborative scientific advancement. The term supremacy itself carries problematic connotations and may overstate achievements. Mainstream reporting rarely discusses error rates and error correction challenges in depth. There's minimal coverage of the quantum volume metric that measures both qubit count and quality, and insufficient explanation of the gap between current noisy intermediate scale quantum NISQ devices and fault-tolerant quantum computers. As researchers at the Quantum Economic Development Consortium note, quantum supremacy demonstrations are primarily scientific milestones with relatively little immediate bearing on commercial applications. Despite these controversies, quantum computing continues to advance rapidly, with significant implications across multiple domains. The most immediate and concerning application is in cryptography. Quantum computers could potentially break most modern encryption systems, enabling what security experts call harvest now, decrypt later attacks. Even a quantum computer with less than 1% accuracy could be useful for decryption, since keys can be verified instantly. This threat has spurred the development of post-quantum cryptography standards by NIST and other organizations, though experts like Dennis Mandich warn these may not be sufficient when AI and quantum computing combine for cryptanalysis. More positively, quantum computers show promise for materials simulation and discovery. Magnetic materials used in medical imaging, electronics, and superconductors could be designed more efficiently. Pharmaceutical research might accelerate through better modeling of molecular interactions. Looking further ahead, quantum computing could transform chemistry and computational biology beyond what AI systems like AlphaFold can achieve. As Mandich explains, atoms and molecules are inherently quantum structures which can only be precisely modeled with quantum computers. The combination of quantum computing with artificial intelligence might lead to breakthroughs in machine learning, financial modeling, and optimization problems across industries. The quantum computing landscape has become increasingly global and competitive. IBM is investing $30 billion over 5 years in quantum development. The Chinese government is building a $10 billion national facility for quantum research in Hefei. Colorado has emerged as a surprising hub, boasting the largest concentration of quantum computing companies globally. Market projections suggest the global quantum computing sector could reach $125 billion by 2030, with North America currently leading but Asia showing the fastest growth. After examining all perspectives, what can we conclude about humanity's progress toward true quantum supremacy? The evidence suggests we have reached what might be called a narrow or contested quantum supremacy. Demonstrations that show quantum advantage on specific, often contrived problems, but with ongoing debates about their significance and reproducibility. D-Wave's claim of supremacy on a useful problem represents potential progress, but the substantial pushback from the Flatiron Institute researchers indicates we're not yet at uncontested practical quantum advantage. Several major challenges must be overcome before quantum computers can reliably outperform classical ones on practical problems. 1. Error correction at scale. Creating enough high-quality logical qubits for complex computations. 2. Quantum algorithm development, designing algorithms that exploit quantum properties for useful tasks. 3. System integration, building complete systems that include quantum and classical components working together. 4th, verification methods, developing better ways to verify quantum results without classical simulation. Based on current trajectories, we can estimate these time frames for quantum computing milestones: 2025 to 2027. More demonstrations of quantum advantage on specialized problems: 2027 to 2030. First practical applications in materials science and cryptography, 2030 to 2035. Fault-tolerant quantum computers with hundreds of logical qubits. 2035, plus widespread commercial applications across multiple industries. However, these projections come with significant uncertainty. As we've seen repeatedly, both quantum hardware and classical algorithms can advance in unexpected ways, shifting the quantum advantage threshold. Conclusion: quantum supremacy represents both a fascinating scientific milestone and a moving target. While headlines proclaim quantum supremacy achieved, the reality is more nuanced, a series of incremental advances contested by equally impressive classical computing improvements. What's clear is that quantum computing is no longer theoretical. Working quantum computers exist today, performing calculations that challenge our most powerful classical systems. Whether they've definitively crossed the supremacy threshold depends on definitions, methodologies, and perspectives that continue to evolve. As we navigate the International Year of Quantum Science and Technology, we should approach quantum supremacy claims with informed skepticism, recognizing both the remarkable achievements and the legitimate contestations, the revolutionary potential and the practical limitations. The quantum future is coming, but like the quantum particles themselves, its exact position and momentum remain subject to uncertainty principles of their own. Thank you for joining us for this critical analysis. Until next time, keep questioning, keep learning, and keep exploring the frontiers of science and innovation.